Okay. Exergy, exergoeconomic, and environmental analysis of novel solar and biomass-driven trigeneration system integrated with organic ranking cycle. Introduction. With the aim of getting insight to help fighting climate change, this study proposes an integrated system for providing all the energetic requirements to a commercial or industrial building through CCHP system, combined cooling, heating, and power. This system sizes the energy contained in biomass combined with solar energy in three ways: electric generation in an internal combustion engine using gasified rice husk, electric generation via organic Rankine cycle, and water conditioning, heating and cooling using a lithium bromide aqueous solution. Biomass simulation. The gasification process is simulated in Aspen Plus using Fortran coding based on the concept that minimizes the free Gibbs energy in the product stream, which contains CO, CO2, CH4, and water. The operating temperature for this process is 120 Celsius degrees. The syngas obtained is fed to an internal combustion engine to generate electricity. Organic ranking cycle simulation. The solar energy is stored as heated water in the storage tank. The heated water is circulated through a heat exchanger to get energy for vaporization of the working fluid of the organic ranking cycle. The vaporized fluid is fed into an expander that has an electric generator coupled. The working fluid exiting the expander goes through a heat exchanger to give its latent heat to a tap water stream. Air conditioning system simulation. The water vaporizes in the evaporator at low pressure, absorbing heat from the surroundings, cooling water for air conditioning. The lithium bromide solution absorbs the water vapor in the absorber, releasing heat that is used to heat AC water. The diluted lithium bromide solution is pumped to the high temperature generator, where heat recovered from the engine exhaust and the cooling jacket is supplied in order to separate water from lithium bromide. The water vapor is condensed, releasing heat, which is also used to heat AC water. Methodology. The methodology used for exergy analysis begins with the estimation of physical and chemical exergy of each stream based on its components. The physical exergy of the pure gas is calculated based on the enthalpy and entropy of the gas at the initial and final stages. The physical exergy of the mixture is calculated by the summatory of the fraction of the gas by the physical exergy of each component. Then the exergy flow of the stream is found by multiplying the molar exergy of the stream by the molar flow. The physical exergy of the water stream is calculated using the heat capacity and the water and of the water and the environment temperature. On the other hand, it is necessary to determine the chemical exergy of each stream, multiplying the fraction of each component with the chemical exergy of each component plus the term RT0 ln y. Finally, the total exergy flow of the stream is calculated by the addition of the chemical and physical exergy in each stream. For the exergoeconomic analysis, a process flow diagram is developed showing all the streams that come in and out each component of the system. For example, for the component internal combustion engine, the fuel equals to the exergy flow of the stream 9 containing a branch of syngas. The product is made up of the summatory of the exergy flows of the streams 18, 19, 27 minus the exergy flow of the stream 20. The investment rate is calculated using the investment in the component, the operating and maintenance factor phi, the cost recovery factor, and the number of operating hours. The cost recovery factor depends on the discount rate I and the service life N. For the exergoeconomic analysis, it is required to use the relative cost difference RK, which depends on the exergy cost of the products and the exergy cost of the fuel, and the exergoeconomic factor FK, which depends on the investment rate, the cost of the fuel CFK, and the exergy destroyed.
Next, we have the results of the study. For example, the first two strings corresponding to the dryer, they have the highest exergy value. The string 4 has a value of 0, and string 13b has a value of 0.001. The study was for two scenarios. For example, in the next slide, we have the equation for the exergoeconomic cost equation uh, for different position. Uh, it's very important for use to a program such as EES. In the slide, we have the uh, cost for exergoeconomic along with their auxiliary equation and the capital investment cost. Research proposed the respective computational models for various types of equipment. In this study, the cost estimation equation for the following components we select were the capital investment, the CRF is the capital recovery factor, the factor phi is operating and maintenance factor, the N is the number of operating hours, and I is the discount rate 0.0615, and the N is the service life, is 20 years. In the figure shows that the difference in the UEEC between the fuel and the product of each component is similar to the difference in the UEEC. However, a more in-depth analysis revealed that in winter, the UEEC of both the product and the overall fuel is considerably higher than in summer. Have two scenarios, in summer and the winter. Finally, we have the conclusion. First, the components with significant levels of exergy destruction with AC, SC, ice, and HX, and they exergy destruction radius in summer and winter with different percent in order. The exercise efficiency of ice and ORC power generation were 25.53% and 95.21% in summer and winter, respectively. This indicates that OREC power generation is superior to ice power generation in terms of energy efficiency. Number two, improving the performance of G, ICE, SC, AC, and HX system should be prioritized based on exergy analysis using structural theory of thermoeconomics, with particular emphasis on AC. to reduce the UEC of ORC electricity generation. The performance of the AC spheres be improved. 3. According to the exergoeconomic evaluation criteria, the ACHX and the ICE system showed significant potential to improving their exergoeconomic performance. Therefore, efforts should be directed toward reducing their investment cost. Finally, however, this study still has some limitation. For example, the weight of the components was estimated using relevant empiric formulas, which may affect it to accuracy for exergo-environmental parameters, such as the environmental impact related to the components during the exergo-environmental analysis. Therefore, to improve the accuracy and practical guidance of the exergo-environmental analysis of the investigated system, future research will focus on improving. Thanks.
Thank you